Okay, so we're going to take a look at some proportion stuff, just like we've been dealing with. Only this time we're going to look at problem solving with some geometry applications. You know, for you guys, actually, I felt kind of bad. I feel like yesterday I should have maybe reviewed a little bit after spring break. That became evident when we got down to the lab. I almost wonder if we should take just a second with this group and just take a quick peek at a couple problems.
Go to that closet.
Okay, so we already know about the cross product property. A couple other properties we want to be aware of. These two are going to show up on the assignment. So look what this first one is saying. It's more important to see what you can do than know the formula. If I start off with the ratio A over B equals C over D, there's a property of proportions that says, that's fine, that says I can exchange diagonal. So I can take the B and the C in this case and flip them, swap them, and the ratio still is true if I do that. So if I do that, I end up with A over C equals, then I get a B on the top and a D on the bottom. And sometimes that's really handy to do. Okay, so that's one new property we want to use. We can exchange in a proportion diagonally. Free to do that. The other one is, and there's a way I want to show this to you that makes more sense. Because this one looks a little weird when you just see it on paper. But, oops. Yeah. Okay, so what have we done here? If I start off with A over B equals C over D, all I've really done, would you agree that if this is an equation, I'm going to maintain the equality of both sides. In other words, I haven't broken any rules as long as I do the same thing to both sides. For example, I could add the same number to both sides, right? Why not add 1 to both sides? Is it true that A over B plus 1 must equal C over D plus 1? Agreed? Treated both sides equally. If I have an equation to start with, if I add 1 to both sides, it's still equal. Both sides are still equal. Well, this is all I've done in getting from this step to that step. If I want to add A over B, the fraction A over B to 1, if you go back to kind of pre-algebra and algebra 1, how do we add fractions? What do we always have to have? Common denominator. So if I want to add A over B plus 1, I have to multiply the 1 by B over B, right? So that's the same thing as saying A over B plus B over B. And on the other side of the equation, I would have C over D plus 1 in the form D over D. So I get the same denominators, right? Well, what does that give me then on this side? I just get A plus B over the common denominator, B, equals C plus D over the common denominator, D. That's all we did, right? So this property of proportions, A over B, if A over B equals C over D, that's the same thing as saying A over B plus the denominator over itself, right? I've just added B over B, which is 1. Same thing over here. C over D plus D over D, but written with the common denominator. Just added the same number, which is 1 to both sides. If you think of it that way, it's not nearly as confusing. Otherwise, that's kind of a weird one to remember. I mean, it's, what are they doing there? That's all we're doing. Just adding 1 to both sides. Okay? All right, so let's use those. Maybe. Oh, I know. Okay, so for example, here, if we want to, what if the question said, and they should have probably written the question down here. If this is true, find the ratio P over R. If I want to find P over R, I could, true, we could have done this, yesterday or the day before if I just cross multiplied and wrote P in terms of R and then divided both sides by R. But there's a lot of algebra. All I have to do is use that new property and just exchange diagonally and I'm done. Okay? I can swap the R for the 6 and then P over R is 6 over 10, which just reduces to 3/5. Okay? Okay, you're going to get some stuff like this, some geometry problems on here. What if they tell us some stuff about this? They tell us we've got this triangle set up here, and we know that the ratio of AB over BD, so that segment, the length of that segment to the length of that segment is the same as the ratio of AC to CE, right? And we're supposed to find the length of BD. We're given all this other stuff. How could I do that? How could I set up a proportion here that would allow me to do that? Okay, so the left side is going to become 16 over x. Good. What about the right side? Is x 10? I mean, maybe, but probably not, right? We don't know that for sure. What's the problem though? Now I need to get AC. Do I have AC there? It's not giving me directly, is it? Can I calculate it though? 20. How'd you get 20? Yeah, okay, if the whole distance from A to E is 30 and CE is 10, well then we know that this must be 20, right? 30 minus 10 would have to give us that quantity. Right, so there's our little trick. So we could turn that into a 20 over 10, and that's easy. From there on out, it's a piece of cake. Just cross multiply and solve for x. Right? No biggie. And there's the steps we just went through. So if we cross multiply, we get 20x equals 160. Divide both sides by 20, and I get x equals 8. There we go. Okay, geometric mean. Here's another thing. This is pretty cool. Geometric mean. If I set up two ratios, the geometric mean is the number that's going to act as the denominator of the first ratio and the numerator of the second ratio, but make the ratios equal to each other. So any two numbers are always going to have what's called a geometric mean. So for example, let's say that we want to take, let's say we want to find the geometric mean of 2 and 8. Okay, what that means then is it's not a normal mean. The arithmetic mean is what we call a regular average. And a lot of times when we talk about the mean in math, we're talking about not this, but we're talking about a simple average. How do we normally find a mean, an arithmetic mean? Add them, divide by 2. So in this case, 2 plus 8 is 10. Divided by 2 would be 5. 5 is the number that's halfway between 2 and 8, but a geometric mean is different. Geometric mean means that we want to set this up so 2 over x equals x over 8. Right? Now this is kind of handy because then it's keeping this proportional. Where this ends up being useful is when you want to scale something up. We'll look at an example here in a little bit where you see how this applies. How could I solve that though? They give you a formula, but it's easier to not even worry about remembering the formula. How do I solve for x there? I've got a ratio equation, a proportion. What do I always do when I solve for a proportion? Cross multiply. Absolutely. So if I cross multiply, look what happens. I'm going to get x times x is x squared. So x squared equals 16. 2 times 8 is 16. So what's x equal to? Okay, it's written plus or minus 4. But which is the one that's obviously going to be in the middle of 2 and 8? 4. So x is 4. We could check it. Does that work? If I put a 4 back in this, is 2 over 4 the same ratio as 4 over 8? Yeah, it is, right? Okay, so that's what it means when we refer to a geometric mean. And of course, if you just do this in general, if we don't worry about the specifics, but we just take the general form of a geometric mean of two numbers, a and b, if I were just to solve this equation, look what happens. If I cross multiply, I just get x squared equals a times b, so therefore x would equal the square root of a times b. And that'll always work. Okay? So if I want to find geometric mean of 8 and 18, I would just take the square root of 8 times 18, which is 144, so I get 12. And that works. 8 twelfths is a 2/3 ratio, so is 12 eighteenths. So this would be useful if you wanted to, for example, have two pieces of paper, two sizes of paper that were, one was bigger than the other, but they were proportional, right? If I want the ratio of the width to the height to be the same here as here, then I could set this up as a geometric mean problem, right? 210 over x would equal x over 420. So the height of this one becomes the width of this one, right? And if we do that, x squared equals this big number. And if I take the square root of that big number and make a decimal out of it, it comes out to be about 297. So that would have to be the height of this sheet and the width of this sheet if we want that one to be proportional. Okay? Make sense? All right. Last thing. Okay. Proportions in real life. And this is real intuitive. Everybody kind of knows how to do this stuff, just naturally. If we want to know, for example, this is kind of an interesting problem. Let's say that we have a scale model of the Titanic that's, it's an exact replica. And we want to know how wide it was. If we know that it was, roughly how long it was. Say we know that it was 882.75 feet long. Maybe we knew it was roughly 880 feet long, something like that. We want to know how wide it is. Well, if I take this scale model, I can set up a proportion here that'll allow me to solve that pretty easily. If my scale model is 107.5 inches long and 11.25 inches wide, then doesn't it make sense that I could set up the width of the actual Titanic divided by the width of the model would equal the length of the actual Titanic divided by the length of the model? And I could just solve that thing. Is there another proportion that would make sense to you? That's one way to do it, but there's another way that seems to make just as much sense to me. I could say the real width over the model width equals the real length over the model length. What else could I do? Yeah, okay, good. I could say real length over real width equals model length over model width, and that would also hold, wouldn't it? Either way, I'm going to get the same answer if I cross multiply. Okay? And if I just plug in x for the unknown, which is the width of the Titanic, it's really simple algebra. Right? If I plug that stuff in, cross multiply and solve. It's k. So how wide is it? Let's find out. If I just cross multiply and solve for x, I get about, what? About 92.4 feet. Big deal. That's how wide it is in the middle. Wow. Okay? Make sense? That's it. All right. Is it worth going anywhere? Okay. I don't think so either. So I've got a little puzzle for you then. This week's puzzler.